Okay, so this week we'll cover all the data types first, especially fixed point, floating point, and also vectors, some basic combinational blocks for Tuesday, for today. And there will be a quiz on some basics. Two questions are very similar from the in-class one, and one question is for just model a very simple combinatorial logic using 3 different methods. And then we'll cover another modeling method called hierarchical method. We'll talk about how to create a wire to make the connections in submodules at the top level. So that's for today. If we still have time, I'll let you guys work on your homework assignments. And on Thursday, because today's the tutorial, data types tutorial is pretty simple, so hopefully we can get it done as soon as possible. And then there will be another new tutorial on Thursday. Will be more practice on combinational blocks and applied on IPGAs. So there will be a lab. We'll talk about the lab this afternoon. And there's another homework assignment which is due in February. So it's going to be the week after next week. And there will be another quiz on Thursday as well, right? So it will be quiz 2 on Thursday on floating point. So please pay attention to the floating point data type today. Okay. So for the fixed point, you probably have learned that in, I'm not sure I have done that before, but you can see the formats for fixed points pretty simple. It's just converting decimal numbers into binaries, sometimes to hex formats. So you're not expecting a lot of materials to be put on the quizzes or exams, maybe just one question or so, because it's just so simple. You can see these UQ 16.16 formats. It's unsigned, 16 for the integer and 16 for the decimal part. And you can see, for example, 14.125, right? So this is a 10-based number. And 14 converted to binary is going to be 1110. And 0.125 is 0.001. Okay, that's a binary format. And to make it comply with this format, it has to be 16 digits for the integer part and 16 digits for the decimal part as well. So you can see this is, it's just adding, trading zeros. And for these ones, you're adding zeros in front of it. It's not changing the numbers. It's really simple for this format. And you can definitely combine them in 4 digits for the binary version to make them in the hex version. So these are the hex version of it. Okay. Unsigned, so no sign. Every single number is binary. So this is the very basic format, UQ 16.16. And for Q 15 point, you can see it's signed, so which means the first digit, this is not 2's complement, okay? So the first digit, the MSB will be the sign. So 0 will be a positive number and 1 will be a negative number. And it's just a sign, it's not a number, okay? Just keep that in mind. So for 14, minus 14, right, you have 14 here, and because it has to be 16 digit, and then MSB is a sign, so you have 15 digits for the number. It's adding all these 11 digits to be, just add zeros to it, and MSB to be a 1 here. Okay, there's no number after the point because it doesn't define that. Okay, and it can definitely convert its digits into its hex counterparts. As A, this is 00E. Okay, for this one, you just combine this format and also the first example as well. Any question on this? Should be pretty simple, right? Logic 101. Okay, easy. So floating point. Okay, I have to pay a little bit more attention to it. It's going to be on the quiz on Thursday. Okay, let's just get it done today. So think there's a couple of questions for the homework assignments, but it's not due until next week. So you want to study this, make sure I understand it first, and then study it a little bit, either today or tomorrow. So be prepared for Thursday's quiz. All right. So you can see it's definitely used for the fractional numbers, with the integers and for the fractional part. There's a lot of different formats, and we are not doing all of them because a lot of them are difficult to do it manually or on handwriting. But the first one is doable, so we are going to focus on the first one. Examples on the quizzes will be also on the half precision format as well. So you can see 1, 2, 3, 4, and we're only focusing on the first one. So if you know how to do the first one, you will be able to know the following ones. But we don't have to do the following ones. So for the half precision floating point, for the exponent bias is 15 digits. No, sorry, it's 15. And we'll get into the details why we need a bias over there. And number of digits for the sign for S is 1, and the number of digits for E is 5, and number of digits for F, the fractional part, this is exponent part, is 5, and for the fractional part is 10. So total digits will be 16. So the total number of digits for the half precision floating point format is going to be 16, right? So eventually the number being stored in the computer system for the floating point numbers will be SEF. Okay, and there will be certain ways to, the computer is able to understand what's going on, but we just need to store the information of S, E, and F into the memory, so the computer is able to figure out the following ones. Because floating point, it could be something with a fractional part, it could be really long, and will introduce a lot of it take a lot of memory. That's why we convert it to a certain format. So it's SEF. Okay, SEF. Let's take a look at it. For example, 14.125. Okay, 14.125 in half precision format. Okay, so make sure that you know this is definitely signed, right? This is signed because S is a signed bit. So this one is a positive number, so the signed bit definitely should be 0. Okay, so S is 0, easy. It's 1 digit. Why? Because on the table you can see there's 1 digit for the signed bit. For the exponent bit, it's going to be 5 digits, and there's the bias. And the bias being used is 15. So no matter what you're getting for that E, you just have to add it to 15 as a bias to form that binary number, the 5-digit binary number. And the reason for that is sometimes this becomes negative. So you always have a bias. You have something to subtract from, right? So we'll look at the next number after this example. But now let's just look at this example over here. The 14.125, the first step, right? So first step converted to its binary counterpart. So 14 is going to be 110, and 0125 is going to be 0.001 in the binary format. So no matter what you are getting, right? For this one, you do have an integer part, okay? And there will be another example without the integer part. We'll have a different way to deal with it. But for this one, what you want to do is you shift that point to just right after the first one, right? Right after the first one, like this one. Convert it to 1 point something. And you count how many digits it shifts from 1, 2, 3. So that 3 shifts of the point. And so it becomes 2 to the power of 3, 2 to the third power. Okay? And that one here, this becomes the E digit. So you see this is to the third power, so E becomes 3 plus 15. Okay, if this is 4, it becomes 15 plus 4. so on and so forth. Right? And you keep the rest to be the f part, the fractional part. If it's not making up 10 digits, you just add some trailing zeros to make up 10 digits. So now you have 6 bits over here, right, for the fractional part. So the 4 more zeros. All right, and then so see you have S is 0, that's a sign, and E is 18 because it's a bias plus the exponent, which is 3 over here, right? So it becomes 18. So you convert it to binary, it's 10010. And the fractional part is you just directly copy this part in here and make up 10 digits by adding 4 zeros. And that's everything for the final result. It's SEF, right? So S is 0 is the sign, E is a bias plus the exponent of 2. Right? After shifts, you count it how many times it's shifted. And F is just the fractional part. If it's not enough, not more than is not 10, then you add several digits to make up 10 digits, which is here. So this part, which is the fractional part, and adding 4 trailing zeros. So eventually, you can see 1 plus 5 plus 10 plus 1 plus 5 plus 10 will be eventually 16 digits, and that forms SEF. That's the real number being stored in the memory for that floating point. And because you have some of you have learned logic or VLSI, you know these memory units are just holding a 1 0 over there, right? How could you tell where the point is if it's a fractional number? They're just storing 1 zeros. So I have to store any fractional number in a certain format so the computer understands what's being stored in there. So when it's looking at it from the memory, it understands that the whole thing over here, from here, right? From here to here, these are the fractional part. Okay? And they know these ones are the exponent, right? How many digits being shifted, and this is the sign. It's just different format. Very similar to two's complement, right? So we design a rule to represent a certain number or even negative numbers. Make sure the computer is programmed so it's able to understand what's going on in the memory being stored in the memory. Any question on this? And after combine all these digits over here, it can group them in 4s and convert into a hex.
So the exponent bias allows us to have negative exponents?
Yeah. Here's an example over here. Good question on that. So I have an in-class over there. Quiz. So I have a negative counterpart of this same number over here. You can see negative 14.125, right? So definitely. Oh, actually, this is not. I'm just talking about. So when we use a bias, it's actually designed for the numbers are less than 1, right? That's one of the questions on the in-class. That's answers the question. It's for, not just for negative numbers. It's for any of the numbers less than 1. Let's look at the example for now, okay? Just since we are talking about it. So for example, this number, okay? So the integer part is gone, but we still have the fractional part to be the same one. So 0.125, right? 0.125 is 1/8, right? It's 1/8, right? So 1/8 means it's dividing 2 by 3 times. You got a 1/8, right? So divided by 2 by 3 times, so you are shifting that point by 3 times. So that's why you are getting a 0.001 in binary. That makes sense? You can see a lot of numbers we use in the examples are either 0.5, 0.25, 0.125. It just make it easier to convert it to binary. Okay, and for this number, it converted to binary of this guy, and follow the rule that the point has to be behind that first one. So eventually this becomes 1.0, but the thing is we are shifting the point to the right instead of to the left. So in that case, we have to times 1/8, which is 2 to the negative 3rd power. Okay, so now you have a negative exponent, and you add it to the bias. So now you appreciate the positive bias over there because you have something to subtract from, right? So then it's 15 minus 3, you are getting 12. All right, so it converts 12 into its binary counterpart. Remember, it has to be 5 digits. So 12 is 1100, but we need 5 digits, so we add a 0 in front of it to make it 5 digits. And definitely this is a positive number, so as 0 and E, we just got the result over here, 01100. And we don't have, so after this part, after we shifted the point, we don't have any ones in the fractional part after shifting. So the fractional part should be all zeros. Okay, keep in mind, you're not looking at the original numbers fractional part. You're looking at the fractional part after shifting. Okay, so it's all zeros. And combine all the 16 digits together and group them in 4s, are able to get this number over here. And the hash format. So for a negative number, it's a lot easier compared to this one, the fractional number only, because it's the same number with the absolute value of the first example, but only had the sign changed, right? So all the rest should be the same, but only the MSB being toggled, and that's it. I'm gonna see the final result is changed from 4B10 to CB10. And I think that's everything we need to know for this part of the content of the tutorial. Okay, don't want to spend too much time on it. And there's a computer, I think there's a software online, it's a Google search, and there's a form calculator can be opened up in the browser. And you can verify your result over here by picking up the half precision one. It's a floated toy. It's just a calculator. So I put the results over here and I got this verified. Okay. And ASCII code. So most of you did the microcontroller with me last semester, so we all know ASCII code, right? So the ASCII code is from the keyboard, or especially for serial communication, when you are sending a character, right? So it has its corresponding 8-bit or byte representation, and that's all the numbers you can find in the ASCII table. Right, so I think these are the LSBs of the ASCII code of the byte, and these are the MSBs. All right. I think we have a different table over there somewhere else, right? It's easier to look at, but this one is fine. It's just making everything more compact. So I'm gonna ask some of you guys, right? Just please answer that question. So for example, just make sure everyone knows what's going on here. So for example, what about what's the ASCII code for uppercase E? What is the ASCII code for uppercase E? It's here, right? 4-5. It's E. And you look at the MSB, it's a 4. And lower 4 bits is 5. This is 4-5. All right, so probably I'm going to use this table on the exams or quizzes in the future. Okay? So make sure you understand how to read it. Or lowercase a. 6-1. Right, 6-1. So there will be a keyboard experiments later in the semester, so we are going to use these a lot. Okay. Sometimes you'll see a Z, high impedance, is not, it's not 1 nor 0. It's just a high impedance is usually unknown, or 2.5. If it's a 5 volts, it's probably 1 volts. VDD for the IPGAs is going to be 0.5 volts. Or it could be open circuit or disconnected. It's just nothing, okay, high impedance. So we do have these different values. 0, 1, X, don't care. It could be 0, 1 or nothing. And high impedance is Z. And there's the integer type. Sometimes we have an integer. You can see integer type in the example and some of the examples. So the integer type you can put in the Verilog is 32-bit long. Just keep that in mind. Just 32-bit for integer. And vectors. Sometimes it could be confusing because sometimes the vectors, the bracket, a number, colon, another number, they are being placed in front of the letter or in front of the variable. Sometimes behind the variable. You can see when we are trying to declare all these ports and everything, the brackets and numbers and all these columns are being put in front of it. In front of it. So keep in mind, when you declare the variable or the vector, so this should be in front of that variable. In front of the variable. So you are defining that this guy is a vector instead of just a 1-bit wire or 1-bit register. It's a vector with 8 bits. It's from 7 to 0. It's 8 bits. It's a bundle of wires instead of just 1 digit. So in that case, when you declare this guy this way, the MSB is going to be bit 7. So usually we do it from left to right. So the left one, the most left digit will be bit 7, which is the 8th bit, and it's going to be the MSB. So the one on the left will be the MSB. So for this one, bit 7 will be the MSB, and bit 0 will be the LSB. If you declare this variable or vector this way. For this one, it's a 4-bit variable or vector. You can see the MSB is a bit 3 and LSB is a bit 0. What about this one? I see, hey, the bit 7 is always MSB. Is that the case? No. So if you do it this way, it's actually bit 0 will be the MSB and bit 7 will be the LSB. What's the difference? How do I understand it? It's actually pretty simple, right? So if you declare everything this way, and when you assign a, let's say, let me write on paper, for example. It's actually really simple. Yeah, because when you have to access the single digits, some of the digits in the vector, you have to know where they are, right? So that's the key point here. So if you do a 7 to 0 vector like this, right? Or 0 to 7 vector. I give a 0x FE. What's the difference? So FE is right. So for this guy, it's just the bit 7 is over here and bit 0 is over here. And for this one, bit 0 is over here and bit 7 is over here. That's it. So when you access it, if you want to take out the 1 is the 0 here, you just have to do a vector 7. Pretty simple, right? Just from left to right. Just align to the hex number or to whatever the binary number is, right? Depending on the width of it.
Is there a reason why you'd ever set 7 as the first bit, or as the least significant bit?
Is there a reason you want to set this as a first bit?
Yeah.
Yeah, that's just a convention. I think this is more common. Very rarely we do it this way. I mean, this is handy. Just sometimes you want to assign, for example, you are keep using the same data, and you just want to assign it reversely instead of this conventional way. You can just directly modify here instead of modifying the data. So I think sometimes it becomes handy, but it's just giving you some options when you program it, right? So your question is why we are doing this as the first bit?
Oh yeah, but it makes sense now, just to be able to have the option.
Yeah. So this is just making up a vector, right? And so if you make a vector, it's actually a space. So for this vector, it's basically just 8 flip-flops, because they're able to hold the data there. So it's 8 flip-flops, and when you are assigning its parallel data over here, you get 8 parallel data, and you have 8 flip-flops. It just directly assigns these values to these latches or flip-flops. And we usually declare the vector this way. So MSB here, so start with a bigger number and 0 on the right hand side. That's the convention we declare a vector in Verilog. Probably 80% of the time we do it this way. Okay. So there are some examples of assignments and shows you the concept. It's the same concept as whatever I just introduced. I mean, run the simulation, you'll see the results over here. I think, see here, right? So for this one, I had an FA, and for this one, I have FA as well. And so in Verilog, you can definitely simulate this for the results of the waveforms. You can see a 1 or 0, but if you see something like this, it's not like analog waveform display unit, right? It's not a monitor showing the analog voltages. So whenever it's not 0 or 1, it has to use something like this to represent it, right? It's a bundle of wires. You have to click it to expand it in order to see all the single digits, but there will be 8 wires, but they put them together. There's no way to display it because this is not 0 or 1. So it's FA. FA is 4 ones and 3 ones are 0, right? The number we wrote on paper. And no, so FA is 4 ones and 1010. 1010. So 10, right? So they just drew it this way, a box. So if you zoom in, it usually looks like this, right? So I have 2 data, for example. Right? It's a data. Like this. FA, whatever, FB, if it's not a 1 or 0s. Okay? But you can see that it's FA, FA. No difference. It's just different locations. If you expand it, it's going to show you the from bit 7 to bit 0, these are FA, all these digits. And for this one, it's going to be from 0 to 7, it's FA, right? It's just directly assigning from left to right, to the certain locations. Nothing fancy here. And there are some examples shows how to use these operators. I think we already covered most of them last week. These are really simple blocks. And there are some examples, for example, a home alarm system. It's nothing but just some practice on Verilog. All right, so we haven't done that too much. Let's give you some really simple examples how this work. Before we get into that, let's see if we answer all the questions on the in-class. Okay, so only the first one haven't been covered yet. Let's move down here. And that's from the first tutorial, actually. So we have learned structural, data flow, and behavioral. And hierarchical is not totally a different new method. It's just using a certain way to make connections to the submodules. So look at this example. Or let's directly look at the example on the in class. Probably easier for you guys to get it done. For this guy, right? Or I have the code over here. So for this common logic, you have these many gates, and these are sum modules. So I think this is a really good example because repeating the inverter for once, as you know that if you get this done, you can keep using this for millions of times. Like when you did the VLSI one, right? You create a module for the ALU. You probably have, I don't know, like 100 inverters or 100 gates. Did you create 100 different gates by yourself in the library? No, just did it once, right? And then you can just directly drag and drop. So same concept. So when you are making a little module, you just imagine it's just a cell. It's just basically a cell. It's being put in the library. Whenever you need to use it, just grab it. You can grab as many as you want. It's the same stuff. So now let's see. I need an AND gate, I need a OR gate, and I need a one inverter as well. Okay? To create the library. So I can keep using them. So first time I got a module here. I do AND gate. Module AND gate ABC. And for the lower level, the name of the ports doesn't matter at all. They are not being exported to the higher level. It's the same concept as all the cells, VLSI cells, right? You have all the names. No matter what name you want to give to them, it doesn't really matter. You can always rename the ports at a higher level after you reuse it. Does that make sense? Because imagine that if the lower level ports are being exported to the upper level, what's gonna happen? There will be like millions of same names the ports. They will be physically shorted to each other because all the ports of the AND gate are being called ABC. So they shouldn't be exported to the higher level. So you can see A, B, C. I just name it whatever I want, right? Just A, B, C for the AND gate. And you are not even seeing C here, but I do need a C because it does have 3 ports. And I can just simply use the data flow method and use the assign A and B to C and then modules. So simple, right? Just to model a very simple AND gate. Done. This could be a standard cell in your library. You can keep using it for as many times as you want. Doesn't matter. And also I need the OR gate to be modeled. You can see the OR gate is being modeled as well. Same concept, but just change the operator in the middle. Change from AND to OR, and that's it. Okay? And then I need an inverter. So inverter is just a NOT gate. AB, AB, and B is A NOT, and N module. That's it. So I'll let you guys start writing the top and bring all these together. And I'll let you tell me what the problem you'll see. I do not need a second AND gate to be modeled. I can directly just declare it or instantiate it twice in my top, right? And you can make certain connections. You can make sub-connections in your top. I'll let you guys do it first before I let you see the solution over here. How would you do it? Module, right? I'll call it digital circuit. How many ports do you need over here? How many ports? As a black box. You could put the inputs and outputs in the parentheses at the first line, or you can do it later. Doesn't matter. A, B, C, and Y. Should you use different names of the ports? No, because it already tell you this is A, B, C, Y exactly. But for this guy, since I don't have a name label over here, you can use different names for the outputs. Intermediate wires, doesn't matter. Okay, semicolon. So input, what are inputs? A, B, C. Output Y. Okay, now let's instantiate the AND gate, for example. So it has to be exactly this name. Keep in mind, saw issues from the in class last time. You have to use that name. Exactly. So it'll be AND gate. You can name it, right? I'm gonna do AND gate number 1. Dot. Remember, right after dot is the signal line where? From where? From the top or from the sub module? Even though they have the same name, but from sub module. This A is the sub module's A. Is this A? Not this A. Okay? Then this is supposed to be connected to the top A. Similarly, can you change the line? Yes. Just don't forget the comma here. Sometimes you can see people just directly write it down as a list. This is actually easier and better. I prefer this. So in Vim, you can just directly list it in a certain way. But in Vivado, I don't believe you have to press a lot of space. So this is a dedicated editor. It's definitely a better option. So just keep listing over here. Dot, sub modules port, top port, comma, new line. You can keep writing behind it, or you can change the new line, which is a better option. This is more user friendly. Dot B, sub module B, top B, comma. What about next? Dot sub module C. Do you have an option in the top? No. How could you solve that problem? You can put a wire. So you can always imagine a wire data type. It's basically just a piece of wire, floating wire like this. It's floating there. When you create a wire, it's just a floating wire. It's like you grab a piece of wire in the lab and just throw it in the system. It's floating there. I have 2 terminals. You can connect to 2 terminals, right? To make the connection. You can do a wire, right? How do you call the wire? Let's make it more clear, more intuitive. Let's call it AND out. Okay? AND out for the first one. So C should be shorted to what? AND out. Similarly, you need to create a wire for this guy, and you need to create a wire for this guy. And I'll let you guys to do it. I'll give you 5-6 minutes to get this done. All right. So you basically need 3 wires. You need a piece of wire here. You need a piece of wire here. So when you do this, when you are declaring or instantiate the AND gate 1, or this gate, you use this wire for once. Actually, this is done, right? This is done. Semicolon. And I'm going to show you this as well. So when you do the OR gate, because this is the OR gate's name, has to be the same name. And then you name it OR underscore 1, number 1, right? And dot, the sub modules wire is A. A is shorted to where? AND out. So you use this little piece of wire twice. So we are looking at the 2 different instances. I can tell, hey, AND out, the same piece of wire is shorted to both C and A. So what's happening is, so it's making a connection from here to here, and from here to here. So it's indirectly shorting A and C through that wire. because this A is C is shorted to one end of the wire, and A is shorted to the other end of the wire, so that eventually being bridged between the 2 points. What's that?
For AND gate, you have it as C is the AND output, isn't C an input? Why would we be output?
This one?
Yeah.
Season
Yeah,
output
because-
for the AND gate.
Yeah, see the output for the AND gate,
I see.
right?
You did kind of switch conventions from the tutorial. Because in the tutorial, your outputs and your function declarations, like in the modules,
Hmm.
you put the outputs first and then the inputs afterwards.
Hmm. Even
Is there a-
even for here, or in here.
In there, yeah.
Oh yeah, it doesn't matter. So order here doesn't matter.
But shouldn't there be kind of isn't there generally a convention?
What's the convention to follow the order?
Yeah.
Yeah, to follow order, you just have to have within your module, the sub module on the top, they have to follow the same order, right? I mean, the convention, it really doesn't matter. Input first, output first, doesn't really matter. I have seen both. Yeah, but it's just the thing is, if you follow a certain order here, if you don't want to use this name associated, right, or named association, how do we name it? Named association or order association, right? So if you're using order association, so you don't really show the sub modules ports over here. It just directly list all the tops ports in a certain order, trying to match the sub modules ports, which is highly unrecommended. It's not really readable, so we have that example in the tutorial, but we don't really use it. So we just need to use it whenever someone else wrote it and posted it online. We're looking at all these codes. We know what's going on. That's the only case. But if you are doing this named association, then we don't really care. The order doesn't matter as long as we make the connections in a certain way. It's already declared here, defined over here. All right. And also, like I said, you could just, I usually I like modeling everything this way, because when I'm designing a digital block, I know the names of the inputs and outputs. I'll directly just to get it done. When I'm typing, I just want to type it quickly. I just module, some module. Oh, so I need 5 ports. I'll just directly put the parentheses and the 5 ports, right? And after that, I come down here and then I start thinking about like which one should be input, which one should be output. Sometimes I have to modify. I'll come over here to change it, so I don't have to worry about anything in the parentheses anymore. It's just your preference. Whatever you have to do, it's both are fine. You can either define it over here in the parentheses, or you can do it afterwards. Okay. But sometimes you can see here, if you put all the inputs and outputs down here, you are not keeping this list very long. And sometimes if you have define all the input and outputs in the parentheses, this can be long, right? So it's just to list everything down here, we can make it shorter. It's another benefit to consider. Any question about the top?
For the OR gate,
Mhm.
we use the not output wire.
Mm-hmm.
Is it okay that we use the not output wire before defining that the not gate?
The wires defined over here. Usually you declare the ports and you declare the wires as well.
So we declared the wire, but then in the following we use the OR gate.
Yeah.
And we use the not output.
Yes.
Then the next line we define the not output using the not gate. Does that make sense?
No, you define it here, right? It's already defined, so you can directly use it.
Even if it has no value.
Well,
No
you should
values,
go,
there's no.
AND gate, and then not gate, and then OR gate.
Yeah, that's what I was thinking. Does it matter if they're swapped?
It doesn't actually, because everything is like a picture. It's like a snapshot. Just it's different from the C language. It's running from top to bottom, right? So everything's like a snapshot.
So, because this is
It's gonna
hardware,
synthesize. Yeah,
it
it's
can
gonna
just be
synthesize.
like a mess if you want. Like it can just be random order, and it'll still do it.
Yeah,
in terms of the gates.
for the always block, for the behavioral, sometimes it does, but most of the cases like a combinational block, that's definitely not. It's just like a snapshot. It's done. It's a hotwire, piece of hotwire. It's done there.
I'm not going to, but would we be able to put the top module at the top and then
Doesn't matter.
some modules?
No, it doesn't matter. So for example, we have different modules in the same file, right? You could also put the modules in different v files, .v files, and the .v file's name doesn't even matter, right? You can name, for example, example1.v, but within that .v file, you name the module to be this name, and this is name you want to use for the instance over here, not the .v file's name. So you can name the .v file whatever you want. Sometimes I'm thinking it's magical. I mean, how could it be able to see inside the file the name of the modules? And it actually works. As long as you put them in the same directory, right? The same directory have all the .v files, and they will be able to see the module's name inside the file. Interesting, right?
Yeah.
Yeah. And for example, like something like this is really simple. You can see I could even put all the modules in one .v file. I think the name of this file, or the one in the tutorial is called first system, right? You can keep all the modules and the tab in the same file, like what I'm doing here. So all these could be in one .v file. So you don't have to create like a bunch of .v files to make it really stressful. It's just one .v file. I have all the modules. Just have whatever I have here. Just type them up in one .v file. So module. You know, have n module, right? And then you have a tab to wrap up these three modules and make the whole thing into one digital block. And that whole thing here can be used for other modules. So this whole thing here can be used as a sub-module for somewhere else. You are creating a different .v file. You are writing another module down here. It's actually very simple, right? For example, you have two. After this is done, for example, I'm drawing a box over here. This would be a duplicate of this guy, right? And I need another one here as well, and I need another one over here as well, right? So 3 of these. So there will be 3 Y's, and this has ABC because that's the same, it's a duplicate, and I'm shorting these to here and got one more Y here. Right? You can write another one, so you can imagine you have to create 3 different wires in the middle, and so you can indirectly connect the output to the inputs by connecting both to the same wire. Okay. So the 3 pieces can be shorted. The outputs can be connected to the inputs of another one, and have final outputs. There will be like 9 inputs and 1 output. This can be another top module. You can keep going. It's unlimited. There could be like, I don't know, hundreds of layers, but eventually get down to the transistor level circuits. This is what we learned in the VLSI class. So for the VLSI, you can see for IPG and logic. It goes down to the gate level, right? So the gate level circuits. We never go deeper than that. For VLSI, we get down to the C5 layers level, right? So those substrates and everything, have to understand the layers, and then transistors, right? And for microcontrollers, it's just a C level, right? We don't understand. We don't really understand what are in the blocks.
So after you draw all the wires connecting the gates, would your Y just be a knot, or would we use a not gate at the end to get the wire out?
This guy?
Yeah, that guy at the end.
Yeah, because this is a port. Your tab, right? This is the tab module.
Yeah.
Your tab has a final output, right?
Yeah.
So the final output is just shorted to the NOT gates, B. So basically, you need another like a dot B versus Y.
Okay, so that's it. So after we do like the dot B, it's done. Or
Yeah, dot B versus Y, you're done. Yeah.
Okay.
Yeah. So you just need 3 modules, and you have to use the NOT gate twice. But you have to have a different name for it, like NOT 1, NOT 2, right? Yeah. That clear on this one? This technique. Okay. I think the in class 3 is done. Any questions on in class 3? Any more?
Again, on question 6, the wire type vectors being used by these followers.
Yeah.
Doesn't have what follows?
That's a mistake. I'm sorry for that. Yes, it's just that example here. This is just one I showed you, right? It's super simple. Just a wire bracket 7 to 0 and 0 to 7. That's it. We already explained that.
Did you wish to explain both of them?
No, it's just this. Just this.
Just the first one? It's input 7 to 0?
Yeah. So it's going to be wire. 7 to 0. Yeah, that's it. Sorry. So this is a declaration here. So I'm declaring a wire to be this, and the name of the variable is A. And wire this, the name of the variable is A as well. So when you access to the certain bits, remember? So when you declare it, that's a type, right? Data type. And that's the name of the variable. It's the number of bits and shows you the locations of the MSB and LSBs, all the other bits as well. So when you access to the bits inside, this has to be behind that variable. For example, A5, right? So you can use it and access it. All right, that's everything for the data type and floating point. Let me check the assignments really quick, see if you guys are ready for that. I think you will. You will be ready for that. And LEDs and switches are independent. You don't have to use a switch to turn on the LED because these are different connections to the FPGA. And there's a constraint file that I need to explain to you guys really quick. Let me see if I can find it here. I probably posted to the lab. Check really quick. Here. So this afternoon when I do the lab, you can see the download the constraint files. You need to download it. It's over here. Extract. Alright, so that's the constraint file. And when you are doing your FPGA design, you have to include it in there. Let me open it up in the editor so you can see what's in there. So the constraint file defines the connections or the names of the FPGA physical resources that I can use in your Verilog. So for example, like something like this. Let's start from the top. So you can see the clock. So that's the name of it. So if you use this wire here, it's actually being used as a port of the top. So clock has to be lowercase CLK, and that's a 100 megahertz pin. It's a physical pin on the FPGA. You don't have to really spot it on the board. It must be somewhere. It's a very thin wire and connect to the crystal, but it's definitely creating 100 megahertz, and you know this is existing somewhere on the board. So what you can do is when you are designing a system, let's say a subsystem. Here's a sub module, for example, and this sub module requires a clock to do the always add something, rising edge of the clock to do something, and there's the output, right? So that's your sub module. And we are writing a top module, and the top is IPGA inside of the simulation you have been doing. Keep in mind, the IPGA now is the top. Now your simulation soft top. Now it's a hardware IPGA top. So when you are writing a top, you still have to start with the module. The module. And you just name it top, for example. Alright. And you are using, for example, just a clock. And you are using an LED, whatever, LED, let's say 0. So both are keywords. You can see CLK is a keyword, LED is also a keyword. Because LED 0 is over here, you can find out, hey, LED bracket 0 is a physical pin available on the IPGA. Right? Cannot be uppercase, has to be exactly the same name over here listed on the constraint file. So clock is another physical resource you have. Okay, and then this name, for example, is called digital circuit, whatever. Let's just call it digital circuit. Underscore circuit. And then you instantiate this guy. Okay. And I would like to connect the clock to the 100 megahertz clock over here. So what's the name of this clock? CLK. Right? For your sub module, it doesn't have to be CLK, it can be anything. Let's just say sub. Okay? CLK sub. They could be the same name, doesn't matter. But usually we just call it clock. Just make it the same. Make it easier. And I want to connect our subsystem clock to the 100 megahertz clock resource on the board. Because it's already have a keyword here, I don't want to change it. So it's basically just a dot, clock, dot, sub, underscore sub, and connect to the physical clock on the board. And I'm connecting the output dot Y, which is the sub module's Y. I want to connect to LED 0 so I can see it blinks. Oh, I don't have two ports, so I can have a parenthesis over here and then semicolon. So the top, as IPGA top, is very simple. You don't need to assign signals to it. If you want to make it complicated, you can definitely write a variable coding here to modify or control the behavior of the clocks and everything. You can even add a always block over here. But at the IPGA top, you can see I'm actually just making physical connections. Instead of using my hand manually make the connections with wires, I just code it up. It's just making connections. So you can see I know I have a clock with 100 microhertz on the board, and the name of it is clock. And also I have a LED as a display, and the name could be LED 0. If I'm trying to use a 8 bits, I can even have LED 7 to 0. And then I started making connections. I have to instantiate. Oh, forgot the name. DOT, right? DOT. Okay, just put a name here. So the digital circuit is a Verilog module we already wrote. And I instantiate this guy over here and name it DOT and make the connections with the clock. And so your 100 megahertz clock will be delivered to the subsystem. So this guy, if you have a always block inside of the sub module, you are doing always at the falling, rising edge of the clock, and then do something, and it will be able to be driven by this 100 megahertz clock. So in that case, you don't have to write a simulation file in there, and a lot of times it won't be allowed because it's a physical hardware. And you can see there are a lot of other things on the constraint file, right? You can see clock, switch 0 to 7. Oh, actually not. Switch 0 to 15. There are 16 switches. Even though the switches are next to the LEDs, they are not interconnected, keep in mind. The LEDs are display modules as outputs, and switches are inputs. You could also use inputs. Right here are switches, right? Switches. If you have an AND gate here, connect to output is AB, right? ABY, AND gate. This is switch 15. switch 14, so on and so forth. So this guy and this guy. It could definitely make connections over here. So you can use 2 switches as the inputs and 1 LED as the output. You can form a little AND gate and you can demonstrate on the IPGA board. Right? So switch on, you got a 1, switch off, you got a 0 for the inputs of the AND gate. Okay, you can do this and see the output. Alright, so in that case, for this example, you need more ports over here for the switches. And you do need to define inputs and outputs as well, right? Inputs, outputs. So you need to add switches. A lot of times we don't really do them individually, just make it simple. Sometimes it reports errors. It's a bit inconsistent. So a lot of times since we know we have all the LEDs and switches available, let's just we usually just do this, right? We just declare everything. Just declare everything. For example, input, it's 15 to 0 SW. Output is 15 to 0 LED. And when you access to the single digits, to the individual digits, you just don't have to use all of them. For example, you only use 2 switches. You just use these 2 switches to access these switches by putting this number after the name of the vector, right? Same to the LEDs. So there will be a lot of examples in the labs tutorial, so you can definitely refer to these ones. But just let you know that the constraint file is something you want to work with, and you have to come back and look at it all the time. And very interestingly, sometimes the synthesis, it happens only 1%. I don't know why. I have seen this several times in the past. So after it runs all the design, they downloaded the constraint file from my website without any problems. They extract the files and unzip it and then load it to the IPGA, and just showing errors, couldn't run. And eventually they go back to the constraint file and open it up. Half of the lines, half of the constraint file contents are getting deleted. So if you see issues and everything looks right, but you're still not getting the results, come back to the constraint file and look it up. See if you still have everything over there. If not, go back to my website and re-download it and re-extract it. It should be able to solve the problem. You can see this one has everything in here, right? These are all the physical resources on the board. It's actually really helpful to look at, so we know what are really in there, right? So you have LEDs. Just talk about that. And 7-segment display is something we're going to cover in the next few weeks. The display module as the outputs. And that's the point. There's the point of the 7-segment display. And there's a control unit for the as a switch for each display module. And these are the buttons, right? Buttons. So the buttons are inputs. The button center, button underneath, button left, button right, button. Oh, this is button up, button down, button center. These JAs are GPLs. This give you a lot of flexibility to design your own system. So the JA ports, JB ports, JC ports, JD ports, JC ports. So all these ports are GPLs. If you design your own digital system, you can always use these GPLs as ports. They're just the physical ports. Okay, nothing else. It's not being shorted to any of the physical resources on the board. And these are the ADC's ports, the analog inputs, wires, already designed for these. You cannot use these ports. And these are the VGA ports. What is this? RS, RX. So these are the PS2 for the keyboard, for the USB keyboard interface. And SPI, that's for the onboard memory. It's not an SPI we're going to learn later this semester. It's just something else we don't have to worry about. And that's it. You can see not too much. So we can expect what we're going to do this for the whole semester. Any questions on anything before we do the quiz? Can we don't do the quiz?